recording. Yes. Share screen. Okay, so now you can actually see my screen. It seems to work. Okay, so last time we started with the introduction to the standard model. We're still going to continue with that. I'm going slightly slower than I was hoping, but I think this is fine. Because again, it's not so much about how quickly we go and how much material we cover, but how well you get the main point of what I'm saying. So, you know, because if you end up not covering a chapter, you can always go to the relevant textbook and cover it yourself. But if you've got no clue what I'm talking about, then it's not going to be very useful. So we're still in the introductory part, really. So we're having a lot of jargon. So let's go briefly on what we did last time. Just with an email. Okay, I guess I should not let that disturb me. Okay, so we said that in the standard model, we have 12. Oh. What happened? Nice.
I see a dark screen.
Yeah, I see something bad happen.
Check your cable.
Yeah. Hold on. Wait. Sorry for these technicalities. Let's see if we can share. Cheers. Do you see my screen?
No.
Wait. Okay, hold on. Again, I'm going to disconnect the cable and start it again. Maybe there is a problem in the cable. Again. Sorry for that. Okay, it's okay now? My indication is it's okay.
It's okay.
It's okay. Okay. So we said that in the framework of this, again, there's something happened. I don't like that.
We still see the screen.
You still see my screen?
I see introduction to the standard model.
No, because I stopped seeing. I don't understand what's happening.
Try writing something?
No, I'm not. Wait, again. I'm doing it again. I'm not sure what this is. It looks like some technical problem. Maybe I'm just moving a little bit my computer so that it will. Share screen. Okay, I hope it's going to stay like that and not moving anymore. So we said that there are, in the framework of the standard model, we're talking about 12 fermions, which are the fundamental particles. Right? And then they can interact with it. So the 12 fermions, let's go very briefly. We divide them into 3 generations. Generation 1, generation 2, and generation 3. And each generation contains a neutral lepton. Lepton means particles that do not carry the strong force. So the first generation would be the neutrino electron, the second generation would be the neutrino muon, and the third would be the tau neutrino. And then there is a charged lepton. This will be the electron, the muon, and the tau. And then we have an up-type quark. So this is the up, the charm, and the top, and the down type quark. So this is the down, the strange, and the bottom. Of course, I'm not sure what if the names mean anything. And the charges they carry, so neutral or neutral, the charged leptons are always having a minus charge. It's a convention after all, right? Thomson could have decided that the electron carry a positive charge. The up quark carries a plus 2/3, and the down type minus 1/3. Now, in these 12 fermions, they're known as flavors. So we say we have 12 flavors of particles. I'm not even sure why. But this is the reason. Now they can interact with each other. So the interaction is mediated by other particles called as gauge bosons. So we have several bosons depending on the type of interaction. So for the electromagnetic interaction, it's known as QED, quantum electrodynamics. Then the gauge boson is the photon. For the weak interaction, then we have 3 gauge bosons, W plus minus and the Z. For the strong interaction, you have what's known as gluons, and there are total 8 of those. Because they carry their own charge, which is known as scalar. Now, gravity, and I mentioned that, is not part of the standard model. If it was, then there would be a graviton. In addition, there is an extra particle, which is known as the Higgs boson. This is a spin 0 boson, whose interaction with the other particles is what gives them the mass. And we'll discuss that later on. Now, for each particle, there is an antiparticle. For each fundamental fermion, there is an antiparticle. This follows from the Dirac equation, which we will learn. Okay. Now, the fermions, we have the 3 basic forces: electromagnetic, weak, and strong. But not all the fermions are capable of interacting via all the 3 interactions. So all of the fermions interact via the weak interactions. So if I divide the fermions we made stable into 3 categories, so neutrinos, and then charged particles, charged leptons, sorry, and quarks, and then the fundamental forces are the strong, electromagnetic, and weak. Then all of the particles interact via the weak interaction. Only the charged leptons and the quark can interact electromagnetically. And only the quarks can interact via the strong interaction. Right? Right. So we say, as we say in electromagnetic, particles that interact electromagnetically, we say that they carry a charge. And particles that do not, we say they carry zero charge. So in the same way, we say that particles that interact via the strong interaction carry the strong charge. And the strong charge is known as scalar. The jargon or color charge.
Rồi anh Mạnh. Vì nào?
Is there a question? Is there any question?
I want to ask something about the weak interaction. So it turns out that there's no such thing as neutral weak charge particles.
Yes, that's true.
That's an empirical fact, or is there some underlying mathematical, I don't know, theorem to, and why shouldn't there be, right? All other charges exist in neutral form. Why doesn't the weak charge exist in a neutral form?
That goes beyond the standard model, and honestly, somewhat beyond my knowledge in that. Within the standard model, you're right that there are no particles that are neutral to the weak interaction. I think that in other extensions of the standard model, there are, but I will have to check out exactly to give you a precise answer here.
But this is an empirical fact in that case. We've never seen a particle. Okay.
Yeah, I told you that all the particles, this is one of the sort of an disappointing thing, I would say, is that all those particles were discovered and detected, including the last one that was detected was the Higgs boson, right? It was detected in CERN a few years ago. There are no new particles that are not part of this scheme of this model that were detected, right? Now, as we mentioned yesterday, not yesterday, the last lecture, we do have some observational evidence that the standard model is incomplete. But as far as the particles, and this is where I'm a little bit hesitating, these are all following from symmetries of the Lagrangian. We write down the Lagrangian, and we look at the symmetries of the Lagrangian, and each symmetry essentially would represent a particle. So in order to include new particles, that means that there is some bigger symmetry, which we're not seeing it right now. Okay, right now, experimentally, we don't have any evidence for particles that do not interact via the weak interaction. This is the final and simple answer. We do have, as I mentioned last time, some observational evidence that there is something missing in this entire model. Okay, we will discuss that maybe in the last week of the semester if we have time to discuss. About some of the extensions.
Okay, thanks. The second question, kind of related. In electric charges, we have things like dipole moments and stuff like that. Does the equivalent also exist in the strong and the weak force? And have a color dipole moment?
We do have excitations, if that's what you mean. We'll discuss them. I'm not sure if today or on Thursday lecture.
Okay, great, thank you.
We do have particles. The proton, for example, and the neutron, right? They are made of the lightest quarks, right? But these are the lightest quarks. We said in the quantum field theory framework where we live, these are excitation of a field. Basically, the basic idea is that all particles are simply excitation. But this is the first excitation. The same way if you think of in quantum mechanics, those of you who already learned quantum mechanics, right? You have a wave function which is in the ground state, right, the minimum level, but then you can have the first excited level, the second excited level, etc., which give rise, for example, for the, splitting in the hydrogen atom, etc. So we have the same thing here. The proton and the neutron are the ground state of the particles. But you do have particles which are composed of the same quarks, but not in the ground state, in the excited state. These are the rho pions, the the rho particles and the delta particles. I will discuss those. So it very much resembles what we're seeing. But let's do it in an ordered way. So everything that does not carry the strong quark is known as leptons. So these are leptons. But this is a jargon. We have only 3 stable leptons, right? The electrons and the 3 neutrinos. The stable quarks, now the quarks do not come as free particles. They are, because of the nature of the quantum QCD, the quantum chromodynamics, they're always bound. And bound quarks are known as hadrons. Now, the hadrons can come in 2 types. We have either a mixture of 3 quarks. So 3 quarks, for example, the UUD, right? This will be the proton, right? So these are known as baryons. Baryon is big and strong. Baryon, big. And you also have hadrons that are made of a pair of quark and antiquark, right? UD bar, for example. This will be the pion. So 2 quarks, or pair of quark antiquark. These are known as mesons. Again, this is jargon. It's made of, because they have intermediate mass. They are heavier than the leptons. The leptons tend to be very light, and the baryons tend to be very heavy, and the mesons are somewhere in between. We'll discuss those. Okay, so just for the jargon. Now, we spoke about the fundamental forces.
Question?
Yeah.
That you have a pair of quark and antiquark. Does that mean that they do not annihilate like regular, like leptons, for instance?
Yeah.
Okay.
True. It's different quarks, up and down. Annihilate you can have with a particle and an anti-particle, but the down and this is the down bar, meaning the anti-down is not, it cannot annihilate with the up because it's a different particle. It can annihilate with the down. So you have a down and then anti-down.
Thank you.
Okay. This is a pion. This is a pion plus because the charge will be positive. All right, fundamental forces. Actually, there is a minus sign, but this is some convention, strange convention. Fundamental forces. So we said, and that is the strength of the quantum field theory, is that it solves 2 main problems with the classical treatment of forces. Right? We said that classically, we treat the forces as action at a distance, namely that they derive from a potential, right? If we take, for example, the electromagnetic force between 2 particles, right? I put here a proton, and I put another proton, and I let them approach, right? And classically, I can go to the rest frame of one of the protons. I can calculate the potential. And then from the potential, I can derive the force that acts on the other particle, right? This is what we do in classical mechanics, in E&M, right? Even in quantum mechanics, yeah. But the problem with that is that it violates the special relativity, because it essentially assumes that the information about the existence of the true protons travels at infinite speed, namely faster than the speed of light, right? So, so we want to avoid that, to be consistent with special relativity. The other thing is that within the framework of this classical interaction, there is no way of creating or annihilating particles. You cannot produce a pair of electron positron, and you cannot let them annihilate. So let me just write it down. So classically, action at a distance, or force is derived from a potential, conservative force. So violates SR, because signal travels at infinite speed. And does not allow the creation or annihilation of pairs, which we do see, right? This is something which is seen in the labs quite often. So in the quantum field theory framework, this doesn't exist, right? Because the interaction between particles is always mediated by a gauge boson, right? There is no such thing as action at a distance. There must be some intermediator, right, which is a gauge boson. So, for example, the interaction between, electromagnetic interaction between any charged particles, right, will be mediated by a photon, right? But this is a virtual photon. So you have two electrons coming. And then the first electron emits a photon. So time always progresses in this direction. But this is not space. This is a cartoon. And then it emits a photon, and then it, of course, changes its momentum. And the point is that the momentum is always conserved in each of the vertices. So what we really care about is the vertices here. And then the second photon, this is gamma, this is a photon, right? It travels. There is no arrow here because it doesn't carry any charge. The arrow represents a charge. And then this second photon interacts with the second this photon interacts, it's a single photon, not a second photon. This photon interacts with the second electron, transfers the momentum, of course I'm talking about 4 momentum, to this second electron. And this is how the momentum exchange between the two particles occur. The important thing, so this is known as a virtual photon. Now, a virtual particle is really a quantum mechanical fluctuation or quantum fluctuation, right, which exhibits some of the characteristics of a real particle, but it's not a real. We cannot observe it. Okay, what we can observe the initial conditions here and the final condition here. But we don't know what happens in between. This is just a mathematical prescription. Okay, we got no way of knowing what happens in between. This is the mathematical prescription that helps us understand it and do the calculations, really. Now, because it's a virtual photon, it does not obey the relation between the mass and the energy, right? M squared equals E squared minus P squared. So a virtual photon is also known to be a particle, or virtual particle is called off the mass shell. Because M squared does not necessarily have to be E squared minus P squared. Now, the most important thing is that in each vertex, the form momentum is always conserved. Okay, so if we have a form momentum P1 and P2, and let's say the form momentum of the photon is Q, then we always have that P1 mu is equal to P2 mu plus Q mu. Because form momentum is always conserved in each vertex. So globally, the form momentum is always conserved. Right, that's true for the vertex here, and that's true for the vertex here. So we always have a conservation of the form momentum. That's how we ensure to comply with the rules of special relativity. Also, other quantum numbers are conserved, not just the form momentum. Okay, now, when we speak about interactions, for example, here we have an example of an interaction in which the first electron emits a photon. Because the momentum is conserved, then obviously its momentum must change during this process. And then after some time, this photon is interacting with the second electron. Again, because the momentum is conserved, then the momentum of the second electron is changed in such a way as the total global momentum of the system is conserved. And for an observer that watched the initial state and the final state would simply say, oh, these two electrons interacted with each other. They have exchanged momentum. Now, this can be attracting, this can be repelling. The arrows here just represent the flow of charge, which I'm going to show you in a second. Now, of course, we can have that the second electron is the one that first emits a photon. Which is then interacting with the first electron. This is also a legitimate process. So in fact, when we calculate the probability of the interaction and the outcome of the interaction, we have to sum over all these possibilities. And you see the difference is that here, the upper electron, but here it was the upper electron that emitted the photon, and then this photon later on interacted with the lower electron, and here it's the lower electron that first emitted the photon. Essentially, both of them, represent transfer of momentum from one electron to the other, which we interpret as a force, right? Change of momentum between two particles. We said this is because there is a force between them. again, I stress again, in quantum field theory, this is allowed because the basic entity is a field, and the field is something that exists everywhere. You know, you can think of an electromagnetic field, right? You can think of scalar fields such as the temperature. Every point in space, you know, you can measure a temperature. Okay, so this is an example of a classical scalar field. Okay, everywhere you are, you know, I'm here, I can measure a temperature. I can go here, I can measure a temperature. But there is a temperature everywhere, right? So this is a field. Now in quantum field theory, so you know the field fills the entire space, and the particles are just excitation, quantum excitation of the field. Again, I'm not going to teach you quantum field theory, but this is the basic idea. Now we said that each of the three fundamental forces is described by an exchange of a spin 1 force carrying gauge boson, right? So so for the photon, which is I just described, right? This is the gauge boson for the electromagnetic interaction. These are all spin 1 particles. It's massless, so m photon is equal to 0. And the way we describe it is by this wiggly curve. For the weak interaction, right? Weak interaction is what's responsible for the beta decay, right? This is the radioactive decay, right? The neutron goes to proton plus, electron, and to conserve electronic number plus anti-neutrino electron, right? This is mediated by, we said, 3 particles. These are the, 2 of them are charged, so it's a W plus minus bosons. Right. They have masses of about 80 GeV. It's quite heavy. And the neutral Z boson. So, C0. Slightly heavier, 91 GeV. These heavy masses are actually what causes the interaction to be so weak, because you have to produce these masses. So if you're at very low energies, like we are normally, then it's, we'll discuss that about the coupling constant, the coupling constant. Then this is difficult, so that's what makes it to appear very weak. For the strong interaction, the force carrying particles are the gluons. Oh, I should just mention the W and Z bosons are often being described with dashed line, but sometimes you can see them with a wiggly line similar to the photon. I'm more familiar with this, with the first one, with the dashed line symbol, but I saw that in some textbooks they do appear with a wiggly line. I'm not sure why. I like it that it's being discriminated. For the gluons, it's like a spring. They appear like that. That's the common signature in Feynman diagram. The gluons are massless, so gluon is 0. As we said, that there are 8 different gluons, and each carrying a different color charge. But all of them are still massless. Again, all these interactions originate from symmetry groups. I'm not sure how deep we will go into that. Now, okay, so while the photon does not carry any charge, the W, Z, and the G particles do carry charge, right? Charges, right? The specific interaction charge. So they are affected directly by the interactions. We'll see that. Okay, I think this is pretty much covering what we did last time, maybe going slightly above. So before I proceed, I want to ask if you have any questions. No? No heavier calculations yet, so I don't know. It's mainly just talking about jargon, introducing things. So let's talk about now the Feynman diagrams. So this is an essential part of the language of particle physics, and they represent the transition between the states in quantum field theory. And essentially, they include all the time ordering processes there are. Now, the nature of all these forces and interactions, right? They are depending on the properties of the photons, of the bosons sorry, yeah, from the start. So the nature of all the forces, maybe I should write it down, depends on the properties of the gauge bosons that mediate the forces, right? And the way that they are coupled to the fermions. The coupling between the gauge bosons and the fermions is described by vertices. This is the important part. The coupling between the gauge bosons and the fermions is described by vertices. So the vertices are the building blocks of the Feynman diagrams, right? So for example, the basic process in QED is the emission or absorption of a photon, right? Which is essentially a vertex, right, of 2 charged particles with the same flavor, right? So I can have here an E, but I can also have here a muon, right? So I have 2 charged particles with the same flavor. We have a tau, right? And a photon. So I have 2 charged particles of the same flavor and the photon. This is the basic interaction describing QED. So we always have one gauge boson, one incoming particle, and one outgoing particle. Fermion. But not all the fermions can couple to all the bosons, right? Because a fermion can couple to the gauge boson only if it carries the charge of the interaction, right? So for example, leptons, which do not carry the strong force, cannot couple to the gluon because they don't carry this charge, the strong charge. Okay? I should write it down. A particle can couple to a force-carrying boson only if it carries the charge of the interaction. Charge the interaction. Right. So only quarks carry the QCD color, right? The color charge. So only quarks can couple to the strong interaction, right? Now, all 12 fundamental fermions carry the weak charge, the weak interaction charge, which is okay. So they can all participate in the weak interaction, right? That's obvious. All 12 fermions participate in the weak interaction. Right? But of course, okay. Now the weak interaction charge, also again, it's a jargon. It's called a weak isospin. We'll discuss this shortly. Okay, this is again, it's a jargon. So, some key features of the vertex, key properties of a vertex. So the most important is that the vertex is the position where a particle is created or destroyed. Again, this does not exist in the framework of classical mechanics or electro or E&M, right? But in quantum field theory, it exists, right? So I should write it down. The vertex is the location where a particle is created or destroyed. So, one way to think of that, right here, for example, we said we have an electron which has a form momentum P1 mu, right? And at the vertex, this electron is being destroyed, right? And a new electron, right, with a different momentum, P2 mu, is created, right? And of course, in addition, at the same vertex, also a photon with a form momentum, which is typically denoted by Q mu, is also created, right? So it's perfectly fine. Actually, this is the right way to think of it, because again, we're talking about excitations of the quantum field, that at the vertex, one electron is destroyed, and one electron and one photon are created. Okay, that's one. The second is, I already stressed, the form momentum is conserved at each vertex. This is essential. Form momentum is conserved at each vertex. Okay. So P1 mu is equal to P2 mu plus U mu. Now, not only the form momentum, there are other conserved quantities. Actually, there are several conserved quantities, right? Such as angular momentum, charge, leptonic and baryonic number, strangeness, parity. There are plenty of conserved quantities. There are many other quantities that are conserved as well in each vertex. Right, angular momentum, leptonic and baryonic numbers, parity. There are more. I'll discuss some of those down the line. Now, another thing, I mentioned it, but I need to write it down, is that the arrows that we're seeing, they represent the flow of charge. It's not the direction of motion. Right? Because when we discuss antimatter, the arrows will be pointing in the opposite direction. If you want to discuss, for example, annihilation of an electron and positron, it will look something like that. We have an electron and we have a positron, but the positron, I put the arrow in the opposite direction. And then I can put them like with an arrow like that, and then we have two photons. This is annihilation. Okay, so the arrows represent the flow of charge, not space. And then for the calculation, then to each type of interaction, there is an associated coupling constant. To each type of interaction, there is an associated coupling constant. Again, traditionally, this is also denoted by the letter G. So the coupling constant represents the strength of the interaction. So it's the correct way of thinking of it is as the probability of the spin half fermion to absorb or emit the relevant boson. It represents the strength of the fundamental interaction. Of fundamental interaction. Now, from the coupling constant, we can actually do the real measurements of probability of scattering, of decay lifetime of particles. That we're going to show right away. So, questions? Okay, so how do we represent physical processes? Right, the vertex is the basic building blocks, the basic building block, right, that describe a physical process, right? So from the vertex, we construct the Feynman diagram, which is a graphical representation of the mathematical expressions that describe the interaction between the subatomic particles. Okay, so for example, right, we have interaction between two particles, A plus B goes to C plus D, right? So the interaction would be, as we described, we have particle A, which let's say emits a photon, and then this photon is absorbed by particle, by particle B. So particle A turns into particle C, and particle B turns into particle D. Of course, we can have the opposite, the opposite order, in which particle B first emits a photon, which is then absorbed by particle A, and particle A turns into particle C, and particle B into particle D. Right, so this is time.
What about A becoming D and B becoming C?
A becoming D, yeah, that can happen as well. If the right, well, that depends on the particles. If I'll touch that in 10 minutes. If it's identical particles, then yes, we can have that. But if the particles are not identical, then no. Right? You're thinking in terms of, let's say, electron scattering, but you can think of an electron-muon scattering. Right? Or an electron quark scattering. Okay? Since you have conservation of various quantities in each vertex, then you cannot just have an electron turned into a quark, because you have a baryon number which needs to be conserved in the vertex. Okay? We'll get to that. So, you know, this process involves some exchange of a boson. I wrote it down as a photon, but I want to be general. Now, in fact, yeah, as I said, this is a virtual particle, right? The particle X, we don't see it. So in reality, what happens is that when we do the calculation, we need to sum up over all these possibilities. So we'll simply write down, you know, the diagram that looks like that. I see. Where it's understood, when you actually do the calculation, that such a diagram, you know, we have this initial state, we have a final state, and this diagram really represents the sum over all the possibilities of, you know, time ordered that can happen. So again, I want to stress that we can only measure the initial and final states. Everything in between is really a mathematical tool. In fact, this entire Feynman diagrams are really a mathematical tool, a great mathematical tool, but that's what they are, right? Everything in between occurs at time which is determined by the uncertainty principle, right? So the intermediate particles are virtual particles. They cannot be measured independently. And the Feynman diagram, as presented here, represents all the combination in time of the allowed processes, right? Now, because of this feature, we don't really care about the exact angle that we're putting the X particle, because it's understood that that it represents all the temporal combinations that there can be. Okay. So I can give you, I drawn a few examples, right? So a few examples. Right? So for example, so I gave the example of an annihilation, right? So an electron, an anti-electron, two vertices, we're producing two photons. So this describes the annihilation, namely electron plus positron go into two photons. You have a Compton scattering. Compton scattering is a scattering between an electron and a photon with an exchange of energy. Right? So Compton scattering so I have an electron and a photon. Right? They interact. And then we end up with an electron and photon, but with different energies. Okay, so this is a way of transferring the energy between an electron and a photon. So E plus photon times E. We can have a scattering between an electron and a positron. It is known as Baba scattering. So an electron, positron, we change the photon, and we end up again with an electron and then positron. So we can also have an electron that emits a photon, and then this photon is interacting with the positron. This is E minus, E plus initially, and E minus, E plus at the end. Now, I gave you a few examples, a few basic examples. and the takeaway message, we have a few takeaway messages, right? First, have a look at all these processes representing different physical processes that are actually observed in the labs. They are all made of the same vertices. Now note that the mediator, the virtual particle, does not have to be the gauge boson. It can be the electron. Right? We have that in the annihilation. We have that in the Compton scattering. Right? I just play around with the, just rotate it. So this is, again, one of the nice things that in the quantum field theory framework, these are all treated on equal footing, right? Both the gauge bosons and the fermions. So I've got no problem switching the orders. I should write it down, right? Both annihilation and Compton scattering. The virtual particle is the electron. It can be the electron. So in QFT, this is allowed. For the Baba scattering, I wrote it down with the two different Feynman diagrams because they are inherently different. Right? Remember, time goes in this direction. All right, here we have electron and positron. They merge, producing a photon. The photon then disappears, producing a new pair of electron and positron. And in the lower diagram, an electron emits a photon. And again, we can think of it as the electron is destroyed by emitting a new electron and a photon. And then the photon interacts with the positron, right? So negative electron, annihilate them, both disappear, and we ended up with a new positron. The outcome, again, the end result is the same. We started with an electron and a positron, and we ended up with an electron and a positron. Right? This was the initial condition here and final condition here. Final. But this we can reach the initial and final results via two different mechanisms. So of course, since both these processes can occur, then if go.
Now we can see you.
Yep, we're back.
It was
What's a thunderstorm? That's what happens.
yeah. I can still see the recording, so I hope it's okay.
It's recording.
Well, it's recording, right?
Yes.
Let's go back to the share screen. So I'm sorry for that. It's really strange, Finally went back to the office, hoping that everything here will be easier. It turned out that it's actually
Welcome to Maryland.
works less good than it was from when I'm from home. Is everyone back? There is some rain here, that's true, but I thought that the Barilan internet should be better than that.
The infrastructure doesn't work when it's raining. It's a known problem.
I see. Okay. So going back to what we said, I don't know when you stopped hearing me. So what I said is that when we calculate the probability of this Baba scattering to occur, we must, of course, sum on both possibilities. Okay. When calculating probability of Baba scattering to occur, we must coherently sum. Okay, questions? Okay, let me introduce you to something which could turn out to be useful in the future. This is known as the Mandelstamp Variables. So basically, when we think of a Feynman diagram that involve an exchange of a single force-mediated particle, we can put these diagrams into three categories, right? So let me introduce you. So we have two particles exchanging a single, let me write it down. Feynman diagram involving exchange of a single force mediating particle can be put in three categories. So the first one is called the S channel. S comes from space. So we have one particle interacting with another particle. Let's put it like that, P1, P2. And then there is a force mediating particle. Let's write it as a photon. So I'm putting its momentum as Q. And then this photon again introduces two new particles, which are called P3 and P4. This is called the S channel. S stands for space. We can also have what we had previously, that the first particle emits a photon or emits a Higgs boson. That's momentum Q. And then ends up with another particle, P3. And put the hours like that, so it's P2 and P4. That's known as the T channel. T here would stand for time. And we have a third option, which is the same as the second option, only with the P3 and P4 exchange. That was the one that one of you asked me previously. And that is possible only if it's identical particles in the final state. So if the two particles in the final state are identical, I can switch the order of P3 and P4. And then I end up with a diagram that looks something like that. P1, P2, and then I end up with P4 and P3. This is known as the U channel. So S channel, we're seeing an annihilation process. In the UT channel, we're seeing a scattering process. And in the U channel, we're also seeing a scattering process, but this is only relevant with the particles in the final states are identical. Because the U channel is really the T channel, but this exchange of the particle 3 and 4. So accordingly, we can define the three what's known as Mandelstamp variables. Right. So S is P1 plus P2 squared, which is just P3 plus P4 squared. Definition really T is P1 minus P3 squared, which is P4 minus P2 squared. And U is P1 minus P4 squared, which is just P3 minus P2 squared. These are known as the Mandelstamp variables. Mandelstamp introduced them in the 1950s. Of course, PI are the four momenta of the incoming and outgoing particles involved. The important thing is that all these are, all the Mandelstamp variables are really square of the four momenta. So, four vectors, and the square of a four vector is a Lorentz scalar, which means that all these variables are invariant under Lorentz transformation, or in other words, they get the same value in any frame that we're looking at. Right? All Mandelstamp variables are Lorentz scalars. So for example, we can calculate, and that means that we can calculate them in any frame we're interested in, and we know that they get the same value in any other frame, right? So of course, when we have two colliding particles, then the best is to work in the center of mass frame. So e.g. In the center of mass frame of two colliding particles. Then we have the momentum of the first particle, right? It just be E1, the energy in the center of mass frame. And then let's say it has some momentum, P, Cm, right? That's a four vector. And P2, the four momentum of the second particle, right, is just E2 in the center of mass frame. And then of course it's a minus P, because that's the definition of the center of mass frame. So when we calculate the Mandelstamp variable S, right, it's just P1 plus P2 squared, right? It's just E1 center of mass plus E2 center of mass squared minus P1 center of P is the same P, there's no need for a subscript 1, P center of mass minus P center of mass squared. So this is just E1 Cm plus E2 Cm squared. Or in other words, the Lorentz invariant quantity, of course, S is a Lorentz invariant, so this quantity is the same in all frames. So if we look at square root of S, right, is simply the total energy available in the center of mass, right? Okay, so you'll see that if you look at or you hear a talk by somebody for a particle physicist, they tell you, okay, I'm describing you this experiment. You often see this, what was the S? What is square root of S? This just gives the energy available for the interaction. Now, just two more comments, right? So in an S channel, this is the S channel, right? Then what we really have, right? We have the form momentum of the exchange boson, right? Q mu, right? This is just P1 mu plus P2 mu, right? Which follows directly from here. So what we're really seeing here is two particles, right? We call them 1 and 2. They join together into an intermediate particle, which is produced and eventually is being split into two new particles, 3 and 4, right? This virtual particle is a time-like particle, right? So it's often, the S channel is often drawn, again, approximately horizontally. Now, in fact, the S channel is the only way in which new unstable particles can be discovered, right? Provided that the lifetime is long enough. And what really happens, right, you take two particles, you make them, give them enough energy, and then you're hoping that this new mediated vector boson would be a new particle that you've never seen before. And if it has a long enough lifetime, then you could maybe even detect it directly. Now, as opposed to that, right, the T channel, right, is a scattering. Particle 1 emits boson, and then becomes final particle number 3, and the particle 2 absorbs the intermediate particle and becomes particle number 4. Right, so the virtual particle is space-like. So that's why it's drawn approximately vertically. Okay, that's what I want to say about those. Questions? Okay, then let's talk about Feynman diagrams and perturbation theory and probability. So, Feynman diagram. Perturbation and probability. Probability. So the main issue to realize is that there is, for every process, every physical process that we want to calculate, I mean, Feynman diagrams are essentially a calculation tool, right? We're representing some calculation of a physical process. The problem is that there are infinitely many number of Feynman diagrams for each process, when you think of it, which of course runs into a big conceptual difficulty. Right? For example, right, we describe already, right, scattering of 2 electrons, right? So for scattering for 2 electrons, right? So simplest diagram, we have 2 electrons, right? They exchange a photon, and they're being scattered. Fine. But of course, this is not the only option, right? We can have, for example, an exchange of 2 photons. In fact, you can have an exchange of as many photons as you want, right? There's infinitely many number of options that you can make when you want to discuss scattering of particles, right? From this basic vertex that we have. Of course, in this diagram, in the left one, we have 2 vertices, and in the right diagram, we have 4 vertices. But, you know, we need to sum them all, right? Both of them, we said, you know, these are everything that happens in between is really virtual, so we don't really know what happens. But, you know, both these diagrams have the same initial state and they have the same final state, right? Of course, the difference between the diagrams is the number of vertices. So let me just write it down. So for each physical process, there are infinitely many diagrams that describes it. So in principle, we need to sum them all. When I say sum them all, I mean we want to get, remember, these are just a mathematical tool that help us calculate what is the probability of this process to happen. So each of these diagrams essentially will tell us a number, which will be a probability, right? Or probability of a decay of a particle to another particle, from which we should be able to calculate what is the mean lifetime, right? So when we have infinitely many diagrams, we need to sum the probabilities of all these diagrams, right?
Zaf?
Yeah.
On the virtual electrons in the right, you drew only 1 arrow. Should you have an arrow there or not? Okay, thank you.
That's just because I was speeding up. Electron carry charge, so it has an arrow.
Thanks.
So when we calculate, when we use Feynman diagrams, to calculate. By the way, I can do that in the class. You cannot do that in the exam. Don't forget. I'm kidding. I cannot do that in the class as well. So when we use Feynman diagrams to calculate probability of a process, we must sum over all infinite possible diagrams that describe the process. It's of course quite bad, right? But of course there is a key difference between the left and right diagrams. What is the key difference?
The probability of it happening.
Well, when you look at the diagram, what difference do you see?
Vertices, as you pointed out.
Vertices, exactly, right? So here, the difference is the number of vertices. Right here you have, in the left one, you have 2 vertices. In the right one, you have 4 vertices. And that's a big difference. Because we said that for each vertex, there is an associated coupling constant. That's what's going to save us, right? For each vertex, there is an associated coupling constant. Now, this coupling constant enters into the calculation of the quantum mechanical transition matrix element for the interaction, right? This coupling constant is exactly actually is what enters the calculation quantum mechanical. Now I will define everything properly later on. Quantum mechanical transition matrix element. For the interaction. So for example, right, the diagram on the left-hand side, right, this one contains two factors of G, right? So the matrix element, which is normally denoted by funny M, is proportional to G squared, right? And the interaction probability is proportional to the transition matrix element squared. We're going to learn that hopefully next week, if not shortly. We should start it next week. The interaction probability is proportional to the matrix element squared. Noted by capital gamma goes as M squared, which is just M star. It's quantum mechanical, so it should be proportional to G to the 4. So the more vertices there are, the higher orders of G that we have, right? So if we're talking about the right-hand one, right, we have 4 vertices, right? So the matrix element would go as G to the 4, and then the interaction probability would go as G to the power 8, right? So the more vertices there are, the higher power, higher or larger, the larger power of G appears in calculation of the interaction probability. Probability of interaction. So what saves us is if G is small. So when G is small, then we can simply treat those as perturbations. Okay? So if G is small, we can treat large vertices diagrams as perturbations. That's why, for practical reasons, it's good enough to, in some cases, I'm going to give you the exception in a second, to stick with the lowest, you know, the lowest or most lowest order Feynman diagrams, right? So, you know, a physical process contains all terms, so all the amplitudes must be added, right? So M final There's, M1 plus M2 plus whatever, right? But if for small perturbation, correction is small. Now, just give you some more final comment that since in a scattering problem, the number of vertices is going to be even, right? Then it's often, rather than working with G, then it's often useful to work with the dimensionless constant, which is called alpha. Alpha proportional to G squared. Now for the electromagnetic interaction, this is something which you're, I guess, quite familiar with, or at least you've heard of. This is known as the fine structure constant. Right. I should just say that interestingly, in the literature, alpha is also known as the coupling constant. So there is a double use of the term. Alpha is also called coupling constant. So when you hear about coupling constant, that can also still means either G or alpha. Now in QED, this is the familiar fine structure constant. Fine structure. Alpha is just Q squared over 4 pi epsilon 0 h bar c. It's dimensionless, and this is approximately 1 over 137. So it's quite small, right? So the contribution, so it's less than 1%, right? So contribution from a higher order terms would give you correction of the order of 1% or less. So that's why we can often neglect higher order Feynman diagrams. The problem is that this we can do only for electromagnetic interactions, right? Because in strong interactions, alpha is in fact 1, or very close to unity, which means that it's not a perturbative theory. This is one of the reasons why it's much more difficult to study. However, as I'm going to show you, the alpha does change with energy, so it's not a real constant. It's a faked constant. And when you go to higher energies, alpha actually goes down in strong interaction. It goes up for the electromagnetic interaction. That hence the name running coupling constant. But we won't have time to discuss it today. We'll discuss it on Thursday, I think. So let me just briefly go over other interactions. So other interactions. So we said in addition to QED, we have we have several other interactions, right? Let's talk about the weak interactions. So weak interactions this can be mediated by either the Z, which is neutral boson. So mediated by zero boson, they always conserve the flavor. Right. These are known as neutral current interactions, so it's a jargon. Because they are transmitted by electrically neutral boson, neutral current. But you also have weak interactions that are mediated by the charge boson. So this charge boson obviously does carry charge. And since the charge is conserved in each vertex, right? So when you have interactions that are mediated by charge bosons, then they must occur between fermions who have a charge difference of 1, right? So you can have an interaction between, let's say, a neutrino and a charged lepton, right? So you can have interaction, so they must occur between leptons that have charge difference of 1. So they're not conserving the flavors of the interaction. So these are called charge current interactions. Short CC. So obviously flavor is not conserved.
Is this one charge electric charge or flavor charge?
No, this is the electron charge, right? W plus minus means that they carry an electric charge. So they can couple, for example, an electron and a neutrino electron. Okay. Now,
flavor not conserved?
So flavor, we say 12 flavors, right? Means the species of the particles, right? So electron is a flavor, muon is a flavor, neutrino electron is another flavor, right? Remember the definition. We have 12 flavors. So if we have an interaction with a W, right? That let's say a W minus, right? So we have a mu minus, and then we have a W minus, so that will go into a neutrino muon, right? So this is one flavor, right? Muon is a flavor and neutrino is a flavor.
Okay, thanks.
Right? So the flavor is not conserved.
For this to be a full scattering, the W would then have to meet another particle and change its flavor as well?
Yeah. Or for example, right, it could decay. The W is massive enough so it can decay. So for example, it can decay into an electron and a neutrino electron. It has to be an anti-neutrino electron because the leptonic charge is conserved. So what is plotted here is a decay of a muon. So this represents a decay of a muon into an electron plus 2 neutrinos. Neutrino muon plus anti-neutrino electron. Or it can mediate scattering. You're right. Now this can occur because the muon is quite heavy. So it's unstable. Now let me just finish few more sentences and then we'll finish. I'm a little bit over time, but we had some technical problems, so I'm allowing myself. So I just want to mention that different interactions have obviously different coupling constants, right? So we started the coupling constant for the electromagnetic interaction, right? We simply call it alpha. So it's 1/137. Now, in fact, the intrinsic strength of the weak interaction, so the coupling constant of the weak interaction alpha weak is in fact stronger than that of the electromagnetic interaction. It's about 4 times stronger. It's roughly 1/30. So, you know, naively, you would expect that weak interactions would be much stronger than electromagnetic interactions, right? But this, of course, is not what happens. So, stronger meanings that you would expect to see many more weak interactions than you're seeing electromagnetic interactions. Of course, it's the other way around. And the reason is that the W and Z bosons are very massive. So at relatively low energies, right, the energies that we are looking at in the lab, then it's much more difficult to produce them, so that this really translates into a much lower probability. So effectively, the coupling constant is something like 4 to 5 orders of magnitude lower than that of the electromagnetic interaction, justifying the name of weak interaction. But since W and Z bosons are very massive, the effective coupling constant is something like 4 to 5 orders of magnitude lower than that of electromagnetic interaction. Something like 10⁻⁶ or 10⁻⁷, like justifying the name weak interaction. And the reason, again, is that at low enough energies, then the probability of producing the virtual W and Z bosons is very low. Again, that's one of the reasons why in particle accelerators, we go to higher energies. However, justifying the name right. However, the coupling constant for the strong force is very strong. So the order of unity. And that causes a trouble when it comes to calculations, because that means that we cannot ignore Feynman diagrams of high orders, because they contribute at the same order. Right? So QCD is not a perturbative theorem. But as I mentioned, and I will say a few words more about that in the next lecture, I hope, if not then in the following lecture, then we're lucky enough because the coupling constant is not really a constant. It actually does depend on the energy. And it so happened that for high energies, the coupling constant for the strong interaction decays. The coupling constant from the electromagnetic interaction actually increases slightly with energy, but the coupling constant for the strong interaction actually goes down with energy. So we write it down. However, as it turns out, alpha strong is not constant really. But gets smaller with energy. So that means that at the high enough energies, then this is known as the running coupling constant. Right? And that means that when we go to high enough energies, we can go back and use perturbation theory. It gets better and better with energies. Okay. This is due to the nature of the interaction of the strong force of the gluons, that they can interact with each other because each of them carries a different color. So we'll discuss more about that. This is known as the running coupling constant. And I'll discuss that, I hope, next week. Not next week, on Thursday, I hope. If not, then shortly afterwards. All right, I'm past time. Any questions? Any questions? Okay, if not, then I'll see you on Thursday. I am kind of hoping to finish this part on Thursday. I'm not so sure that we'll finish on Thursday. Maximum we'll finish on Tuesday, and then we'll do a tutorial. Likely will be on Tuesday, and then you'll get the next problem set after the tutorial. Anything else? If not, then have a great continue of the day. And I'll see you on Thursday.
Thank you, you too.
Thank you.
Thank you.
See you.
Let's see that stop recording.